Have you ever wondered if there's more to the universe? What if the very fabric of reality isn't as fixed as we think? What if the speed of light or the strength of gravity was changing with time? What would that mean for our understanding of the cosmos and, well, for the cosmos itself? Everything we thought we know about physics works could be wrong. The fundamental constants of nature, the numbers that control how physics work at its most basic level, may not be so fundamental. And if they are changing, that's good news because it means we get to rewrite physics. And there's nothing a physicist loves more than to turn over old paradigms. So what's the deal with the physical constants? Why are they the way they are? Is there any way we could ever learn more? I'm Paul Sutter and I'm a cosmologist. Let's talk about the universe. These are actually my favorite kinds of episodes to do because the answer to the question, why are the constants of nature the way they are, is we don't know. We don't know. We don't have an answer. These are my favorite episodes because it gives me an excuse to talk about all sorts of interesting angles and issues and arguments, and then we all get to go home and think about what it all means. Before we do that though, please consider subscribing to this channel to get more cosmology goodness because I think you like this kind of stuff too. But anyway, what are the constants of nature? What do they do? What do they tell us? And what do they not tell us? I like to think of the physical constants as little packages, little bundles that cover over our ignorance of how something works. Sometimes this ignorance can be very useful, and sometimes it can be a source of a major headache. And the difference between those two cases is what makes a constant fundamental or not. Let's say I'm a physicist, check, and I want to mathematically model, I don't know, me throwing a ball to you. I start with something I know from physical law or theory, say Newton's laws of motion, which in this case seem rather appropriate as we're about to describe a moving object. Then I list all the things in the universe that could possibly influence the future motion of the ball. There's the action of me throwing it. There's the gravity of the earth. There's wind resistance, and so on. Then I attach numbers or quantities to all of these influences. How hard I throw the ball, the height of my hand when I release the ball, the drag from the air, the downward acceleration of gravity. Some of these numbers are inputs. They define the beginning state of the ball as it begins its movement towards you. But some of them are just numbers. The amount of air drag and the acceleration from gravity don't emerge from Newton's laws by themselves. They just But either way, once I have all these numbers lined up, I'm able to connect my theory, which is Newton's laws, to the real world, which is me throwing a ball to you. Physics done, and it's not even noon. Time for a lunch break. But wait, we start to think as we eat our cheese sandwiches, where did those numbers come from? You know, the ones that had nothing to do with the inputs into the system, the ones that had nothing to do with the stuff under my control. How did we know how to include that much air drag and that strength of gravitational acceleration? Well, the answer is that we measure it. We construct experiments where we measure the acceleration due to gravity. And then we get that number and we plug it into the laws of motion and away we go. And we do the same for air resistance. But that's not the end of the story. We know that it's all physics all the way down. So in principle, we should be able to predict where those numbers come from. We shouldn't just have to measure them. The constants that appear in those equations are just little bundles of ignorance that summarize details that we didn't include in our original attempt to solve the problem. We should be able to find some deeper theory of physics to explain why those numbers are the way they are. And in both cases, that's exactly what we can do. We know that air resistance is really due to the molecular interactions between the air and the movement of the ball through it. The ball is pushing on the air in front of it, and the air is dragging across the surface of the ball. Our number that we plug in is just a summary of all those details that we don't want to bother including in the final analysis because we want to get this done before lunchtime. But ultimately, we know the source of that number. It's a bunch of complicated physics that we could include if we were so inclined. But what about the acceleration due to gravity? Well, that's something we can measure too. It's right around 9.8 meters per second squared. But if we performed enough experiments, we would discover that this number doesn't stay the same. It changes slightly depending on where you are on the Earth, or your elevation from sea level, or any other number of factors. So this number, what appears to be a constant, is nothing but. And here again, we know where the acceleration is coming from. It's due to the gravity of the Earth. And we have a more fundamental theory that describes where that acceleration comes from. Newton's law of universal gravitation. And if we're feeling really fancy, Einstein's general theory of relativity. The reason that it's 9.8 and not any other number is because the Earth has a certain mass and a certain radius. We plug those numbers into our theory of gravity and out pops an acceleration at the surface and we're good to go. But those theories of gravity have an unexplained number of their own. We call it G, or Newton's constant, and it's the strength of gravity. It's how strong the force of gravity is. Once again, we have a number that does not originate in the theory itself, and it doesn't originate in any other theory of physics. We can't go one level deeper to understand where G comes from. It's just G, that number, and nothing else. We can only measure it and plug it in. We can't explain it. This makes G a fundamental constant. Constants appear everywhere in physics. We have thousands of them appearing in all sorts of equations all the time. The vast majority of these constants are not fundamental at all. They're packages of our ignorance, but crucially, we know what we're being ignorant about, and we're making deliberate choices to make our lives easier. I can assign a constant to how bouncy a basketball is, and that constant packages up all the complex molecular interactions that happen when the ball strikes the floor. I know where it's coming from, I just don't want to do all that messy math every single time I try to predict how a basketball will move. But other constants are a little stickier. We don't know where they come from. We don't have access to the more fundamental physics. They're still little bundles of ignorance, but we're not sure what we're ignorant about. That's right. The fundamental constants tell us that we're ignorant about our ignorance. So what are these constants? What are these fundamental numbers? Of course, physicists debate about which of the constants are the important ones because physicists debate everything. Some have lists of 19 numbers, some have more, some have less. Some tried to build categories of numbers like really, really fundamental constants, and then the less fundamental but still important constants, and then others. Some say that the only real constants are the ones that we don't have any units for, the ones that are just bare numbers, like the fine structure constant. Others disagree. But in general, and this is my very own Paul Sutter classification scheme, there are a few groupings of numbers that seem to be helpful to guide our thinking. Some of them have units, some don't. Some of them may be considered derived in the sense that maybe you can combine other constants to form them, but honestly, the precise number in categorization scheme is just numerology to me. It's losing the forest for the trees. The constants represent gaps in our knowledge. They are the places in our very complicated, very sophisticated models that we must fill in from raw measurement, and we cannot derive or explain them. And that to me is the essence of a truly fundamental constant. And so I have fit all the constants into the following 4 categories. One category is the strengths of the forces. This is Newton's G, the fine structure constant, and many other numbers to describe the weak and strong forces which take a lot. A second category is the rest masses of the fundamental particles, like just how heavy is an electron or a neutrino or a gluon or so on. The next category of constants are the properties of the quantum. Planck's constant, which describes the scale at which quantum physics takes over, the properties of the Higgs field, the phase for the QCD vacuum, the strength of dark energy and the cosmological constant, and so on. And then there is the last category, which I call structure of the universe. There are some familiar friends in here like the speed of light. I'm also going to add in here some numbers that you don't often see of tables of fundamental physical constants, like the number of forces, 4, the number of particle generations, 3, things like pi, the number 4, which is the dimensions of the universe, and the number -1, which is the relationship between time and space. Like I said, that's just my own personal categorization scheme. You can make up your own classification if you want, and more power to you. However you divide it up, whatever categorization scheme you use, these numbers share some things in common, besides being important and fundamental. They contribute to Patreon. That's patreon.com/pmsutter, where you can keep this show going, and I truly appreciate all of the support. There's a link down below. No, the real thing that fundamental constants share, whether there are 20 of them or 40 of them, is that they are unexplained. They cannot be derived from some deeper theory. They have no origin, and they appear to have no purpose. The electron weighs this much because the electron doesn't weigh anything else. The electromagnetic force is this strong because it has no other strength. The universe has 4 dimensions because it has 4 dimensions. This opens up some really, really, really big questions. Questions like, are these numbers really constant? As if they never change? And dang it, where do these numbers come from? We're really interested in the first question because it can help us answer the second one. If some of these numbers change, either in time or throughout space, then that tells us that they're not really, really fundamental. I don't know. Imagine if we found that the mass of the electron can change with time. That would tell us that what we call the mass of that particle, what appears to be constant and fundamental, is nothing but. Instead, it's just a reflection of our ignorance of deeper physics. It's like the Earth's gravity or the bounciness of a basketball. It's telling us that we haven't reached the bottom level, the ground floor in our search for understanding in the universe. And let's go with this fantasy a little bit longer. Imagine we do find that one of these constants changes with time or is different in different parts of the universe. We would have a pathway, a route to uncovering what that new physics is. Imagine if we figured out Newton's laws before Newton's gravity. And at first we would have the acceleration of the Earth, and we wouldn't know where it came from. And then we find that it changes with elevation or different parts of the globe. We could use that information to uncover a deeper reality, that of universal gravitation. So, are the constants of nature really constant through all of space and time? Well, it seems that way. Of course, we can't say for sure 100% totally case closed because there are always limits and uncertainties and error bars to what we can measure in the universe. But every test we've ever concocted always comes to the same conclusion. Measuring the constants in the first place is one thing, involving some of the most high-powered and clever experiments we have ever devised. But seeing if they change, that takes volume. Absolute volumes of data, streams of data, rivers, oceans of information. At this point, we're looking for parts per billion shifts in these constants. And there are 2 approaches to getting the volumes of data that you need. You can either get hyper precise on measuring something that changes often, like atomic energy transitions through atomic clocks, or you can get away with less precision, but let the universe do the work for you, like studying something like the extremely early universe, like quasars in the cosmic microwave background, seeing if it's changed at all in the 13 plus billion years of its existence. In either case, what helps us investigate changes in the constants are the very models that we incorporate those constants into. All we have to do is relax the assumption that the constants are constant. Like, okay, we've got Newton's gravitational constant over here in our calculations of gravity. Well, what if it's not constant? What if it goes up or down with time? We can use our models to see what the follow-on effects may be. Or we can assume that the speed of light changes or that the fine structure constant isn't so constant. We can fold that new reality into our theories of physics and predict how, say, the cosmic microwave background should appear, or how many light elements should be fashioned in the early universe. If the gravity of the Earth changed while I was in the act of tossing a ball to you, then its final trajectory, the outputs of the models, will be different. And I can compare what I actually get in real life to version A, which is the constants are constant, to version B, the constants aren't so constant, and see what matches up. Every time we perform one of these tests, whether it's something hyper precise nearby or something big and large far away, we keep getting the same answer. The constants sure do act like constants. The speed of light, the strength of gravity, the fine structure constant, the electron mass, the number of dimensions, pi, like they're all constant. And we see no variations to 1 part in a billion per year here, which is pretty dang constant. Again, I need to make this point loud and clear. Variations in the constants are not ruled out. In fact, we can never rule them out. We can only crank down the precision. We will never, ever be able to prove that the constants really are constant. We can only say they are with ever higher degrees of confidence. But for now, we have to act like the constants are constant and grapple with that. Because the constants being constant opens up not one but two very difficult questions. The first is, where do they come from? And the second is, why do they have the values that they do? And this creates a really sticky, nasty, ugly problem for us. Looks like the constants are fine-tuned. As in, if they had any other value, we'd be dead. Actually, less than dead, which is probably worse. Non-existent. Impossible to be here. Check this out. Let's say we change, I don't know, the electron mass. Just a tiny bit, a few percent. Not a big deal, right? Wrong. This changes atomic energy transition levels. It changes how light is emitted and absorbed. It changes nuclear fusion rates. In a universe with higher electron mass, stars don't form. They can't form. No stars, no planets, no planets, no life, no us. Change the strength of gravity? Big Bang doesn't even get started. Change the dimensions of the universe? Light can't propagate. Change anything, even a teensy bit, and it just goes poof. The history of the universe is completely different, let alone chemistry or even biology. It's all just gone. We're gone. There's no us in a universe with different constants. That's a real whopper of a realization, folks. It feels like we're living on the knife's edge. And if any of these numbers were to change, then our universe as we know it would disappear in an instant. We would disappear in an instant. That's a rather uncomfortable feeling, so I won't blame you if you need to actually sleep tonight and you just pause the episode right here. There are some potential answers, of course, none of which are all that satisfying. The first response is called the anthropic argument. The universe is the way it is because if it wasn't the way it is, we wouldn't be here to observe it. That's it. That's the entire argument. Why is the speed of light like this and the strength of gravity like that? Because if they were different, we couldn't exist. And if we couldn't exist, we wouldn't be around to observe these values of the constants. I mean, okay. I have to admit I'm not very fond of the anthropic argument, but I'm trying to give it as fair a shake as possible. Who am I kidding? The argument may feel satisfying at first, but it's like eating a whole row of cookies in one go, and after a while you start to question your life choices. It's not the greatest argument. It is possible to expand the anthropic argument to make it a little more robust. You can argue that the precise value of the constant doesn't matter. Sure, different combinations of constants would give rise to our kind of life and our kind of consciousness, but maybe different combinations lead to different kinds of life. You know, the classic life finds a way kind of thinking. Like it may be possible to build a universe with different constants, different electron masses and whatnot, that end up with different kinds of life or intelligence that end up asking the same questions as us because they can't possibly fathom our kind of life. They're like, look, we calculated what would happen if the fine structure constant had this value, and then all of a sudden the strong nuclear force is weaker, and you get these things called stars, which would be totally incompatible with life. Isn't that ridiculous? You can imagine that kind of conversation. But this is pure speculation. We certainly don't understand consciousness, let alone life, so arguing that consciousness is going to rise in any kind of universe is going to be a stretch. Ultimately, this line of thinking doesn't answer the fundamental question, at least in the way we hoped it would. Why do the constants have the values that they do? Another possibility is that there's more than one universe, that we live in a multiverse, with each different universe sampling different values of the constants. There are a few extremely hypothetical ideas in physics that can lead to the multiverse. One is through the concept of eternal inflation, where the very early universe never ended its period of rapid expansion, and that different portions of the overall universe pinched off, so to speak, to create their own bubble universes. Another path to the multiverse comes from string theory, where extra spatial dimensions can twist up on themselves in a dizzying number of ways. Each possible arrangement leads to new values of the physical constants and even entirely new laws of physics. The range of possible combinations is known as the landscape, with our universe consisting of one point in that landscape. In these multiverse-inspired ideas, there are a multitude of universes out there that don't support life. But this one does, so here we are. At the end of the day, it's still the anthropic argument, but at least one that explains how different values of the constants can be realized and created, and it explains why we find those values here. There are a whole bunch of universes that each get different values of the constants, but this one produces life, so here we are. There have even been attempts to estimate if our kind of universe is common or not. These calculations run into a whole bunch of issues, the biggest one being that we have no idea what the prior probability is for any particular combination of constants. We can't assume that they're all equally likely, and without that, then we can't assess likelihoods, so all those attempts are doomed to fail because of this fundamental ignorance of the underlying probabilities. So perhaps the multiverse/landscape is slightly more satisfying than the usual anthropic argument, but not by much. But leaving aside the ability to calculate probabilities, there are additional issues with both of these ideas. For one, they are both hypothetical and not supported by, any available evidence. We don't know how regular inflation works and whether eternal inflation is even possible. And string theorists can't make a connection between a particular arrangement of extra dimensions and the physics that it generates, meaning that we can't even make testable predictions. So grounding your argument in unsupported super-duper hypothetical ideas isn't exactly the best way to move forward. What's more, eternal inflation and string theory contain constants of their own that are not explored by different iterations of the multiverse. For example, eternal inflation requires any number of extra unknown parameters to make it work. It assumes that inflation is there and doing its thing and proceeding in a certain fashion, with all of that physics governed by certain constants. And string theory itself has its own assumptions, like a certain number of extra dimensions, a number that is not predicted by the theory. So that doesn't seem like a satisfying conclusion either. No matter what, you still end up with some numbers that you can't explain from pure theory. But that may count as progress if we are able to explain many of our current constants and trim the total number of unknowns down a bit. We may feel like we're getting closer and closer to a fundamental theory of physics, one that is able to explain everything about all the things. But the truth is, we may never be able to get rid of the constants. There may always be bundles of ignorance that we cannot get rid of. I mean, that kind of makes sense. At the end of the day, no theory of physics, no matter how sophisticated, can ever explain its own existence. So maybe this is the limit, and we just have to get used to the ignorance. But that doesn't sound fun. This is what keeps physicists going. It's the belief that there's always more to learn right around the corner. And of course, I have to say that there is the opportunity here for, let's call it divine intervention. It's not exactly physics, which is the whole point of the program, but I'm not going to hold you back because all of our other ideas are, let me see here. Yeah, absolutely terrible. Like I said, none of the answers are all that satisfying. As far as we can tell, the constants really are constant. They don't change in space and time. And however you count them, you will always find a list of numbers that are central, that are core to all of our physical theories. They just exist without explanation and for no apparent reason. And for now, until we find one to change in time or make some major theoretical headway, we're just going to have to live with them. So what do you think? Are we missing something deeper in physics? Is there more to the universe that we're skipping over? Will we ever nail down why the fundamental constants had the values that they do, or will they forever remain bundles of ignorance? Let me know what you think in the comments. It's a big universe out there, but we'll take it one step at a time. Thank you for watching.